Hello. Chapter 3 is about alkanes and their stereochemistry. Mm, why do we learn this chapter? Um, we'll talk about the structure of alkanes, and nomenclature of alkane is the basic approach to naming organic compounds. It provides the fundamental principles of nomenclature of organic compounds. If we learn systematic nomenclature of organic compounds, we can easily draw the structure of the organic compounds by just looking at the name. When we draw the structure by looking at the name, we have to know about the three-dimensional structure of the molecules also. And let's just briefly uh, examine the subject of this chapter. This chapter will introduce the concept of functional groups and alkanes and its isomer structures, also nomenclature, alkyl groups as a substituent of hydrocarbon, and types of alkyl groups, and the principles of naming alkanes. Also, some part of the reactivity of alkanes and conformation of alkanes. Uh, more concept about alkanes and uh, relationship between structure and energies. That's about it. So we'll just briefly explain what the functional group of organic compound is. Let's just take an example of the functional group double bonds. Functional group is defined as the characteristic behavior uh, atomic groups which has the characteristic behavior in all molecules. For example, double bonds in ethylene will have very similar properties as the double bonds in other kind of organic molecules also. This is ethylene, this is methane, but both of these double bonds, regardless of other functional groups, will undergo similar kind of organic reactions. In this case, it undergoes both of the double bonds in these two compounds undergo the addition reactions by bromine. So if we look at the functional groups, and if we can easily identify some functional groups in organic compounds, sometimes it is very easy to predict what kind of organic reactions uh, you have to consider in that organic compounds. So knowing on functional group is very important uh, to predict the properties of organic molecules, also to predict the organic reactions uh, which the organic compounds will undergo. Let's just briefly review what kind of functional groups we learned in this organic chemistry. Here is here's a double bond that I just briefly explained. We'll say about double bond, aromatic, alkyl halide, alcohol, ether, and phosphate, phosphoanhydride, amine, imine, nitride, thiol, and sulfide, disulfide, and various kind of carbonyl compounds like aldehyde, ketone, carboxylic acid, ester, amide, anhydride, and acetyl chloride. Each chapter of organic compound or organic chemistry in this class will cover all this kind, most of this kind of functional groups in later. Let's just focus on alkanes. Alkanes is a compound with the carbon-carbon single bond and carbon-hydrogen bonds only. We say there is no functional groups in alkanes because carbon-carbon single bond, usually carbon-carbon single bond and carbon-hydrogen bonds are very stable and they are inert for the organic reactions. The simple alkane is a methane, which has a structure like this, which has one carbon. If you have two carbons, you add hydrogens, then we can easily draw the structure like this. It is a methane, propane, butane, and so on. If you look at the structure of the alkane carefully, we can easily come up with general formula for the alkane compound, like the CnH2n plus 2, because each carbon has two hydrogens, except two carbons at the terminals, and 2 comes from two hydrogens at the terminals. If they don't contain any double bonds, we call saturated hydrocarbons. And if hydrocarbon contains any double or triple bonds, then we say unsaturated hydrocarbons. We'll focus on saturated hydrocarbon in this chapter. If we look at the structure of alkane, we can classify the alkane structure of alkane compounds into two classes. One is just a straight chain, what we call normal alkanes, or branched chain. Branched chain means it has branches. For example, this is a straight chain. This is a branch chain. Okay, because it has the branches like that. The straight chain is easier to understand the structure and the formula, right? So we'll start with a straight chain. If it has 4 carbons, we call butane, and we can easily draw the structure of the butane like this: CH3, CH2, 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 CH3. But all kinds of alkanes contains only 2 different kind of bonds, CC and CH. So even if we remove the line connecting carbon-carbon, carbon and carbon, and carbon and hydrogen, there is no problem to draw the structures. So most of the cases we use the condensed structure of alkane, such as you remove all these lines and then represent this as a CH3, CH2, CH2, and CH3. Sometimes you remove these lines also and use CH3, CH2, CH2, and CH3. Or sometimes you have 2 CH2s, so you use the bracket and draw the structures like CH3, CH2, 2, and CH3. Right? There are several ways, but in this case, this is the simplest structure for the butane. If we know the number of carbons, we can easily calculate the number of hydrogens you need based on this general formula, right? So if you have 1 carbon, you will have 4 hydrogens based on this formula. If you have 2 carbons, you have 6 hydrogens, and so on. So if you fix the number of carbons, then the number of hydrogens will be automatically determined. So we can classify the hydrocarbons easily based on number of carbons. So if you have one carbon, we call it methane. Ethane for 2 carbon, propane for 3 carbon, butane, pentane, and so on. But actually, this nomenclature comes from the Latin words, but it has very similar. It's a similar pronunciation with an English, like butane looks like 4, pentane like 5, hex like 6, hep like 7, oct like 8, nonan like 9, decane like 10, undecane like 110, that's 11, dodecane is like 2 decane, that is 12, tridecane is 13, and we have a special name for the 20, that's the icosane, and for 30, triacontan. In most of cases, we deal with carbon number 1 to like 10 or 11, right? So we have to memorize from number 1 until 10 or 11, okay? Let's try to think about the structure of butane. Butane has 4 carbons, so it has C4H10. But if we draw the structure for C4H10, we can draw two alkane structures like CH3, CH2, CH2, or we can just move this CH3 to this carbon, and it will become like this. But both of them has the same molecular formula, C4H10. So these two compounds is in a relationship of isomers. Ethanol will be an isomer, but a methyl ether also. Isopropylamine and propylamine, they are in a isomeric relationships. As the number of carbon increases, the number of isomers will dramatically increases also. So for even if you fix the number of carbons in alkane, as the number of carbon increases, you can imagine so many different isomers. We call the relationship between these two isomers is called constitutional isomer, because if you want to convert one isomer into the other isomer, you have to break 2 bonds and move it. So we call this constitutional isomers. It's basically completely different molecules. This is an example of isomers. Because they are isomers, even though they have same molecular structures, they should have the different name. We call this as normal pentane because it's straight chain. We call this as isopentane. It has one branch here. This one also has several branches, but we call this as neopentane, because it's a pentane, because it has 5 carbons. But this is a traditional name, and we have other systematic name also. We learn the systematic way of nomenclature later. Isomeric relationship of organic compound is very important subject. There are several different kinds of isomers. We just learned constitutional isomers, and later on we learn other kinds of isomers like cis-trans isomer and diastereomer and enantiomers. All these cis-trans, diastereomer, and enantiomers belong to stereoisomers. We learn stereoisomers later. Alkyl group is, if you remove one hydrogen from alkane, then there is one bond which on other atoms can be attached. Okay, so that is called alkyl. Usually we reference it as an R. Just replace ANE with YL. YL is objective, ANE is known. Right? This is methane, so if you remove one hydrogen, so one bond is still left and some other atoms can be attached here, then we call this as a methyl group. Therefore, this is alcohol, so this compound will be like a methyl alcohol. This will be methyl amine. We can consider many alkyl groups like methyl, ethyl, propyl, butyl, and pentyl. If you have 6 carbons, we can say hexyl, okay? Heptyl, octyl, nonyl, like that. It is important how many carbons are attached to the how many alkyl groups you have in the carbon. If you have just one alkyl in the carbon here, then we call this is a primary. This is primary carbon, and if it has 2 carbons attached to this carbon, then we call this is secondary carbon and tertiary carbon. Tertiary carbon, and this is quaternary carbons. We can easily distinguish the kinds of carbons in this structure: primary, secondary, tertiary, primary, and secondary, right? And hydrogens attached to that carbon is called here primary hydrogens, secondary hydrogens, tertiary hydrogens. Right? This will be normal butyl. This will be secondary butyl because this is a secondary carbon. This is tertiary butyl because this carbon is tertiary carbon. And this is called isobutyl because this compound comes from isobutane. Really doesn't matter which hydrogen you remove. Even if you remove the hydrogens here, it will be the same as this, right? The same thing goes on here. So we don't have to talk about removing of other hydrogens here. But if you remove this hydrogen, it will be tertiary butyl, okay? Don't confuse. Now, nomenclature of the alkane compounds. If we talk about the nomenclature of alkanes, we use the concept of parent, suffix, prefix, and locant. Locant represents location of functional group or location of substituents. Parent comes from the number of carbons. Okay, suffix represents the kind of functional group. Prefix represents the substituent. Okay, so but if you look at the appendix A, they show that different way. They show that prefix, locant, parent, and suffix. Okay, but both of them are correct. Okay, if we talk about very complicated structures, in that case we have to designate the location of a suffix in the parent carbon. Then we use locant right before parent to indicate the location of a functional group. But in the case, this locant represents location of a substituent, okay, to the parent. And this prefix includes this locant number also. So don't confuse, all right? How do we make a name for the organic compounds? The first, try to find the longest try to find out the parent carbon first. That means try to find out the main chain. Main chain means the longest chain. Okay. For example, here, if you have this kind of compounds, this is the longest chain. So the parent of this compound is 1, 2, 3, 4, 5, 6. 6 carbon is the longest number of carbons of this compound. So we consider this longest carbon as a parent, and we consider this methyl as a substituent, and use the locant for the position of the substituent. When you put the number of location for the substituent, you can start from left side 1, 2, 3, or right side 1, 2, 3. It really doesn't matter where you start. The position of this compound will be the same as 3. So the name of this compound will be 3-methylhexane. Okay. How about the other one here? You have to identify the longest carbon, and this is the longest carbon. How many carbon you have? 7, so it's a heptane, and this 2 CH3 and this H2 CH3 are considered as a substituent. So the parent of this will be hep, and it's an alkane. There is a double bond, so the prefix will be ane, right? A suffix will be ane. Parent will be hept. Suffix will be ane, and prefix is the substituent, so methyl and ethyl. And the location of the substituent will be 1, 2, 3. Oh, one is 3. The other one 1, 2, 3, 4. You can put the number on this carbon from here, starting from here, or starting from the other way. If you start from here, it will be 1, 2, 3 methyl and 4 ethyl. If you start from here, 1, 2, 3, 4 ethyl and 5 methyl. Try to use the lower numbers. So you have to start from the top. 1, 2, 3, 4, 5, 6, 7. Okay, so the name of this compound will be 3-methyl 4-ethyl heptane. Right. So it is important to try to find out the main chain of the compound. So here the main chain is this. Let's practice a little more. And this is methyl, methyl, methyl. So name of this compound will be like 1, 2, 3, 4 trimethyl hexane. Here the main chain should be like this, right? This is the main chain, and this is the ethyl, 3-ethyl. This is also 3-ethyl, but this is 4-methyl. If you start from here, 3, 4, 5, 6. So you have to put the number from the right side. Okay? Numbering with a smaller number of branch points. All right? And then identify the parent compound and number the substituent and use the name of the substituent. As I told you, should be like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So this is ethyl, this is methyl, this is another methyl. So it should be like 7, 8, 9. This is no name. 3-ethyl, 4-methyl, and 7-methyl. Okay. So if you have 2 methyl groups, so it will be dimethyl, 4,7 dimethyl, and 3-ethyl. When you put the order of the substituent will be followed by the alphabetical order. So 3-ethyl comes first, and then methyl comes next. If you have the same functional groups, then if you have two methyl groups, we can say dimethyl. Okay, so this is 4,7 dimethyl. This is 3 ethyl, but 3 ethyl should come first before 4,7 dimethyl. Okay, when you consider alphabets, don't count the di or tri as an alphabet. All right, so you use methyl and M for the methyl, E for the ethyl. So E comes before the methyl, right? Once you identify the parent, substituent, and position, then write the name. As I told you like this. You find out the main chain, and there you have a choice, starting from the left or starting from the right. You immediately know you have to start from the left because the substituent is here, right? Substituent here. And also this compound, this is propyl, but this is 2-methyl, right? This is substituent of this. This is parent, this is substituent, but inside of substituent there is another substituent. This is main chain. So this is like a propyl, but 2-methyl propyl, that's the substituent, right? And arrange the name as like a prefix, and you have the locant in front of the prefix and parent and suffix. So if the parent is decane, okay, it should be ANE because it's an alkane. And prefix should contain the substituent like a methyl, 2-methyl propyl. This can be combined and it will be 2,3 dimethyl, right? And this is methyl propyl, so the name 2,3 dimethyl comes before 2-methyl propyl. So the name will be like a 2,3 dimethyl. This is 6,2-methyl propyl decane. You can practice the nomenclature in the problem set in your textbook. Now we are going to talk about the reactivity of alkanes. Usually, the alkane is not reactive at all. It's chemically very stable. So alkane is, can undergo very few kind of organic reactions. For example, the candle is a hydrocarbon, right? It's an alkane. Sometimes we call it as a paraffins, and paraffin means low affinity compound. So low affinity means low affinity for the chemical reactivity, right? This represents melting point and boiling point of a hydrocarbon. The melting points and boiling points of hydrocarbon strongly depends on the number of carbons you have. As the number of carbon increases, the size of the molecule increases, and melting point and boiling point also increases. The reason the melting point and boiling point increases is because as the size of alkane increases, the intermolecular interactions between hydrocarbon molecules increases because their contact area among molecules increases, and their interaction increases, then makes melting point and boiling point higher. Now we'll talk about the conformation of a hydrocarbon, and the concept of a conformation of a hydrocarbon, concept of a conformation of alkane is very important. We'll start from the simplest one, ethane. There's two carbons. We can draw the structure of anything like this. This is just like, we have to imagine the structure as a three-dimensional entity. Because this is a single bond, you can easily rotate it. If you rotate 60 degree, 120 degree, and then we can get this. 60 degree, we can get this, right? You just rotate this 60 degree, this hydrogen needle goes up, like here, and it'll be like this. This is a modeled structure. But if you look at this modeled structure, we can easily recognize that these two hydrogens, they are in a very very small space, and they try to collide each other. The conformation means different arrangement of atoms resulting from bond rotation. Okay, they are the same molecule, but they may have different conformation. For example, some people can have two arms straight, or they can have two arms inside of their. They can change the shape of their arms, and then the overall structure might be different. Just like a change of your arms in your body, you can just rotate it a single bond, and then you can always make a different conformation. For example, here, if you have carbon, you have an eye here, and look through this carbon-carbon bond, and this black dot is front carbon. This large circle is the carbon in the back. So you have three hydrogens here. You have the front carbon, you have the carbon in the back, and red hydrogens are attached to the carbon in the back. Green hydrogens are attached to the carbon in the front, like this. Then we can easily tell the angle between these two hydrogens, CH hydrogens, will be 60 degree, because this 60, 60, 60, that's 180, and 60, 60, 60, that's another 180, it makes 360. We call this as a Newman projection. We call this as a source representation. Source representation is easy to draw. Newman projection is a little bit difficult to draw it, but it's easy to understand the relationship in the three-dimensional entity, okay? Because we can clearly distinguish front carbon from the back carbon, and we can clearly draw the location of each hydrogens in the front carbon or back carbon, and easy to understand the angles also in the Newman projection. So if you have organic compounds, just first try to draw the source representation and try to convert this source representation into the Newman projection, right? This is source representation, and this is a Newman projection. You just rotate 60 degrees between this carbon and carbon, and we can imagine the Newman projection of this carbon here. In this case, the CH bond in the front in between two CH bonds in the back. This is just, we call this a staggered, because this is like a knife, and they are staggered between these two CH, right? And if you rotate 60 degrees, we can easily tell this is two CH bond. They get closer. But actually this CH bond is two electrons, all right? If they are close together, two electrons will repel each other. There will be a repulsion due to the electron cloud between the CH bonds. Because of the repulsion between CH bonds, here, this structure will be in higher energy than the other structures. We call this as the eclipse structure because this CH is just the eclipse, all right? It's unstable. This is stable. But this stability is this relative energy state. And when we compare the energy bit of these two conformers, we think the energy due to the CH bond eclipsing is about 4 kilojoule. Because you have 3 eclipsed CH bonds, the energy of this compound will be higher, about 12 kilojoule compared to the staggered form, right? Okay. Here, there's one thing that you have to remember. In Newman projection, the torsional strain between CH and CH in eclipsed conformer is 4 kilojoule, right? So if you can count the number of CH torsional strain, you can easily calculate the energy due to the eclipsed stage, okay? Torsional strain is a strain due to electron cloud closure in a three-dimensional space. In this case, there is a torsional strain between CH in the front carbon and CH in the back carbon, right? And that is about 4 kilojoules because you have 3 torsional strains in this eclipsed conformer. The eclipsed conformer will be in a higher energy than the staggered conformer, and the energy difference will be 12 kilojoule. Okay. Here is eclipse conformer. Here is the staggered one. So the energy difference between here and here will be 12 kilojoules. If you rotate more and more, it will undergo eclipsed, staggered, eclipsed, staggered, eclipsed, and staggered. You start from 0 degree. You will undergo staggered, eclipse, staggered, eclipse, staggered, eclipse, and it will rotate 100. If you finish one rotation, you just rotate 360 degrees. This is the energy of eclipsed conformer. This is the energy of staggered conformers. When you rotate from a staggered to the eclipsed, there is energy between staggered and eclipsed conformers. And we can smoothly connect these lines like this, right, to represent energy. If you have the propane, let's try to look at the Newman projection between carbon number 2 and carbon number 3. Okay, this is the front carbon, this is carbon number 2, and this large carbon is carbon number 3. This is staggered form. Let's rotate 60 degrees. And this will be eclipsed form. And then we know this will cause 4 kilojoule energy. This will cause 4 kilojoule energy. But here, there is a collision between CCA group and CH. And the energy due to torsional strain between CH and H will be higher than just the CH and CH, okay? So the torsional strain between CH and CH3 is higher than 4, and it is about 6. So if you compare a staggered conformation and eclipsed conformation of Japan, we can easily understand. We can understand that there is energy difference between these two conformers is 14 kilojoules, right? This is staggered, this is eclipsed, staggered, eclipsed, staggered, eclipsed, and we can draw the lines like this, and we can draw energy diagram between staggered and eclipsed conform of propane. Let's try to think about the butane here. Oh, wait a minute. Yeah. Let's try to think about butane. Okay, here's the eclipsed. This is a staggered one. And I told you this is about 6 kilojoule. This is 4 kilojoules. So the energy difference between uh, this staggered form and this is eclipsed form of butane, there will be an energy difference like 16 kilojoules. Right? In butane, we call this is anti-conformer. This is staggered conformation, but we call this is anti-conformations because these two metal groups are opposite each other. Now let's take a look at this is the eclipsed one, but you can rotate 60 degrees and you will end up this. Uh, in this case, in this case, two metal groups are far apart, so we don't have to consider the energy between these two metal groups because they are opposite directions, they are far away. But here they are a little bit closer. So there is a energy increase due to colliding of these two CH groups, and the energy is about 3.8. Okay, 3.8. You have to remember it, right? Now, so energy of this compound will be 3.8 kilojoules. And if let's rotate to 60 degrees, then it will be like this. And we know the energy of this CH is 4 kilojoule, and this is also 4 kilojoule. But in this case, this is CH3 eclipsed. And CH3H eclipsed, that causes 6 kilojoule. For H and H is 4 kilojoule. But in this case, is CH3 and CH3. The energy of CH3 and CH3 should be higher than 6 kilojoule. And the energy due to eclipses CH3 is about 11 kilojoules. There are so many numbers, all right? But there are only 4. Let's just, this is it, right? This is CH3. Okay, let's talk about the lowest one. HH, that's 4.0 kilojoule. CH3, this is staggered one, but that's 3.8. This is eclipsed one, right? This is eclipsed one, CH3H, that's 6.0. This is eclipsed one, CH3 and CH, that's 11, okay? That's all you have to remember. Now, so let's try to think about the static strain. And here, static strain means the repulsive interaction occurring between atoms that are close, that forced closer together than their atomic radii. So this is anti. This is we call this as a gauche conformation, okay? Because two CH3 are there, both of them are staggered in conformations, but the location of two CH3s are different. In this case, they are far away. They are just opposite. Because they are opposite, we call anti. But they're on the same side. Then we give the name like gauche conformations, right? And let's apply the concept of the energy here. 3.8, 4.0. Gauche CH3 is 3.8. Torsional strain between CH and CH is 4.0. Torsional strain CH and CH3 6.0. CH3 is 11.0. Okay, so in this case, the energy of this one will be 2 CH3 strain, and there's a strike strain and CH torsional strains. So that gives 16. Okay, this is 3.8 because they are Gaussian interactions, and this will be 4 and 11, that becomes 19, and this is the same as this, right? The same as this, and this is the same as this, and this is the same as this. All right, so we talked about the energy of due to the conformer, and we call this energy called strain energies. And the strain energy can be classified into two different kinds of strain energies. One is torsional strain, and the other one is static strains. Torsional strain is due to the repulsion of an electron cloud of the chemical bond. Static strain is due to the bulkiness of atom or atomic groups. If they close together, then they compete with the same space, and so the bulkier group will have more static strains. Try to understand the difference between torsional strain and static strains, and both of torsional and static strain is called the strain energies. This is just a summary of energy cost for the interactions in alkane conformers. HH eclipsed, of course that has torsional strain, alright? I told you it's 4 kilojoule. CH3 eclipsed, mostly torsional strain, but there is some strict strain because CH3 is larger than H. That's about 6. CH3, then there will be a small torsional strain, very large strict strains. That is 11. This is Gaussian. Because this is Gaussian conformations, there will be only strict strain. There is no overlapping of the electrons. So this is purely a strict strain. That is 3.8. Okay, this is about the end of this chapter 3. Let's work off the problem. Throw away as many compounds as you can that are alcohols. Use the formula C4H8O. There are several isomers. Try to draw it. There's no logical way. You have to think about, you have to draw several structures and try to think about the isomers. Okay, here is how many? 4. 1, 2, 3, 4 isomers. There are 4 isomers, right?